So far, we have studied Boyle's law, Charles' law, and Avogadro's law. According to Boyle's law, the volume of the gas according to Boyle's law, the volume of the gas is inversely proportional with the pressure of the gas if the temperature is constant and also the number of mole is also constant. Charles' law says volume of the gas is directly proportional with the absolute temperature of the gas if the pressure and the number of mole of the gas remain constant. Avogadro's law says volume of the gas is directly proportional with the number of moles of the gas present in the gas if the temperature and the pressure of the gas is constant. Now, if all the pressure, temperature and numbers of moles of the gas varies, in that case by combining all these three gas laws we can get that if pressure, temperature and number of mole of gas varies, in that case V is directly proportional to Nt by P, Nt by P, or V equals to proportionality constant K multiplied Nt by P, or PV equals to KNT. Now, K is the proportionality constant and it has been found that for 1 mole of gas, the value of proportionality constant K is same for all gas. Hence, for 1 mole of gas, the proportionality constant K is represented as the R, which is known as molar proportionality constant, molar gas constant, or universal gas constant. Now, the gas equation becomes PV equals to nRT, where N is the number of moles of gas present at T Kelvin temperature under the pressure P with the volume V. So, this equation represents the combined gas equation or the gas equation, where R represent the gas constant. Now, from this equation we already had seen that there are certain limitation with which gases actually follow these gas laws, Boyle's law, Charles laws, these kind of laws. Under certain condition gases follows. In fact, there were gases which shows huge amount of deviations from those gas laws, and these gas equation are the combination of those gas laws. Hence, most of the gases in real life has been found to not follow the gas law entirely. It has been found, in fact, that most of the gas in nature in real shows huge amount of deviation from the gas laws. But the gases in hypothetical term which follow these gas law entirely, those gases has been termed as ideal gas. So these equation, this particular equation is applicable for ideal gas. That's why in the initial part, the heading that I had written is the equation of state of an ideal gas. So this equation that I had derived from combining the gas laws, this is known as the equation of state for an ideal gas. So by definition, the ideal gas we can write gases which follows gases which follow equation of state or gas laws are known as ideal gas. Then what are real gas? By definition, gases which do not obey gas law or equation of state, those gases are known as real gases. It is found that most of the gases in nature, in fact, no gas in nature completely follow gas laws. That's why in nature gases are known as real gases, but in certain condition, real gases can behave like ideal gas. That's why ideal gas equation is important for us to study, to understand the behavior of gases in certain condition, and then we can extrapolate other condition to study the real gases also. Universal gas constant R is a very significant value. The R is can be represented as PV by NT, that is pressure multiplied volume divided by mole number multiplied temperature. Pressure multiplied volume by mole into temperature. Now, the dimension will be for pressure, force force divided by area, that is length square. Volume is nothing but length cube divided by mole into the unit of temperature will be taken in the form of Kelvin scale. Now, length square and length cube will cancel each other, leaving one length, which will leave that force multiply length mean work or energy divided by mole multiplied Kelvin. So the unit of R is going to be unit of energy or work mole inverse Kelvin inverse. Now, different unit of energy and work, by putting them, different values of R can be found. And these are one of the most important values of R: 8.314 joule mole inverse Kelvin inverse, 8.314 into 10 to the power 7 arg mole inverse Kelvin inverse, 0.0821 liter ATM mole inverse Kelvin inverse, and finally 1.987 Kelvin inverse mole inverse Kelvin inverse mole inverse. Now there are few others, all values of R's are there, but these four are the most common one and most useful for our mathematical problems. Universal gas constant R represent the gas constant value for 1 mole of gas. Therefore, when universal gas constant R is divided by Avogadro's number, it represents the amount value of universal gas constant for one molecule of gas, which is represented by Boltzmann constant K. So Boltzmann constant K, by definition known as the gas constant value for one molecule of gas. This is the definition of Boltzmann constant K, which expressed in by this equation K equals to R by Avogadro's number n. So to calculate the value of Boltzmann constant K, you can put the value of R, which is 8.314 divided by 6.022 into 10 to the power 23. This will give the value of 1.38 into 10 to the power minus 23 joule Kelvin inverse, and 1.383 into 10 to the power minus 16 arg Kelvin inverse. Now it has been found that no gas actually entirely obey gas equation, but most gases approximately follow gas equation at low pressure and at high temperature. That is the validity of ideal gas equation. Now, from the ideal gas equation, we can relate the density of the gas with the molecular mass of the gas. Now, ideal gas equation says that PV equals to nRT, where PV equals to N is the mole number and can be represented as total mass by molecular mass multiplied RT, or this can be written as P multiplied molecular mass m equals to total mass m by volume into RT. Now, total mass m by volume is nothing but the density of the gas. So, it can be written as P into molecular mass m equals to density of the gas d into RT. So, the ideal gas equation can also be represented in this form. Can be represented in this form. Pm equals to dRT. Now, from this equation, three different cases can be derived. Case number 1. In case number 1, at constant pressure and temperature, if pressure and temperature remain constant, in that case, M becomes directly proportional with the density. That is, the density of the gas is directly proportional of the molecular mass of the gas if temperature and pressure is constant. What is trying to say is that if temperature and pressure are constant, in that case, for if we compare different gases, the density of different gases will depend on the molecular mass of those gas. The more uh, the gas with a higher molecular mass, gas which is heavier will be more dense compared to the gas which is lighter. This is case number 1. Case number 2 is saying that supposedly I am trying to compare a particular gas, so the molecular mass is constant at a particular constant pressure, and try to see if I alter the temperature, how the density of the gas will change. Now, if pressure and molecular mass is same, because I am considering only a particular type of gas, in that case this entire equation will become R by D equals to P by M by R whole into 1 by T. Now, Pm by R is constant term because a particular gas we are observing, so molecular mass is constant, pressure we have taken constant, and universal gas constant is it itself is constant. So, for this particular observation, for a particular type of gas at constant pressure, Pm by R, this term is entirely constant. This will give D is directly inversely proportional with the temperature. That is, for a particular gas at constant pressure, if you increase the temperature, the gas will become less dense. That's why gases at a higher temperature, if you heat a gas, the more less dense it become, which can be observed for hot air balloon which is filled with hot air. That's why a balloon filled with hot air can go upward in the atmosphere because the surrounding air is much cooler compared to the hot air inside the balloon, which is less dense compared to the surrounding more dense air. So, this is the second case that can be derived from the particular equation. The third case that can be derived is that if both pressure and temperature is altered for a particular gas, in that case the density becomes directly proportional with the pressure and temperature, P by T, because the molecular mass in this case is constant because I am observing a particular gas. In that case, this equation can be written as d1 by d2 equals to P1 multiplied T2 by P2 into T1. This is the equation through which we can observe the state change way for a particular gas. When the particular state is changed for a particular gas, how the density can be changed. So from the ideal gas equation, so far what we have studied is that ideal gas equation combines all the gas equations and produces a particular equation, that is PV equals to nRT, where R is the universal gas formula for 1 mole of gas. Now, we have observed that no real gas in nature actually, no gas in nature actually follow this ideal equation entirely. In fact, on a certain condition only, the gases in nature follow ideal gas equation, and that condition is at high temperature and at very low pressure. Apart from that, no gas can follow the ideal gas. That's why gases known as, which do not follow these ideal gas, are known as real gas, which is most of the gas in nature. And those hypothetical gases which follow this equation entirely, those gases are known as ideal gas, which is a hypothetical which is a hypothetical theory. In nature, there is there is no existence of ideal gas. Also, we can derive this Pm equals to DRT equation from this ideal equation, which relate the density of the gas with the molecular mass, and also the other also with the other parameter, that is pressure and temperature of the gas. And from that, we have studied three cases at where, at the first, when temperature and at constant temperature and pressure, when different gases we need to compare, the heavier gas tend to be more dense and the lighter gas tend to be less dense, as per molecular mass of gas, the density of gas is directly proportional with the molecular mass of the gas at constant pressure and temperature. We also find that if we take a particular gas and at constant pressure we observe the variation of the density with the variation of temperature, we found that the density is inversely proportional with the temperature. And in the last case, for a particular gas, when both the parameter pressure and temperature we alter, the the density of the density of the gas varies according to this particular equation, which says d1 by d2 equals to p1 t2 by p2 t1. Now the next theory that we are going to study is known as partial pressure. Let's assume we have taken a container, and in this container there are gas A mixed with gas B is mixed with gas C. So there are three gases of mixture that we have taken: gas A, gas B and gas C in this particular container. And the total pressure of the gas, the total pressure of this gas mixture that we get is P. Now the component gas A give pressure Pa. The component gas B give pressure to this total pressure, contribute pressure to this total pressure P, Pb, and the component gas C contribute to this total pressure Pc pressure. So all these three gases, component gases, contribute some amount of pressure to the total pressure to create this total amount of pressure. So this total amount of pressure can be written as P equals to contribution of pressure coming from component gas A, which is Pa, plus contribution of pressure coming from component gas B, which is Pb, plus contribution of pressure coming from the component gas C, which is Pc. This contribution of pressure from the individual component gases is known as the partial pressure of these gases. So the partial pressure of component gas A is equals to Pa, and partial pressure of component gas B is Pb, and the partial pressure of gas component gas C is Pc. So by definition, what we can say, by definition we can say that at constant temperature and volume, the pressure contributed by a component of gas in a mixture of gas to the total pressure of the gas is the partial pressure of that particular component gas. So the partial pressure concept is for the gas in a mixture. When a gas present in a mixture, the contribution that this a particular gas produces to the total pressure of the gas mixture is known as the partial pressure of that gas. Let's us take another example. Supposedly, there are two container at same temperature and at same volume. Both the container have gases. One container have gas A and another container have gas B. Now both the container is of same volume, so both the gas have the same amount of volume, same volume, and both the gas are at same temperature. So the temperature and the volume are at a certain we have taken similar temperature and volume. Then we have the pressure of A, Pa in the container, and for the pressure B, pressure for gas B is Pb. When we mix these two, gas A and B, into a third container having the same volume V at the same temperature T, the gas will mix with each other and create a mixture. Now, one thing that we need to remember during the partial pressure, that the mixture of gas that we are taking, the gases that we are taking for creating the mixture of gas, the gases should be non-reacting with each other. That is, the mixture that we have created, the gases that are creating that mixture, the gases should not be reacting with each other. In that case, that in this entire theory of partial pressure will be invalid. So the gases that we are taking in this scenario, A and B, are non-reacting with each other, and we are mixing it into the third container having the same volume V at a same temperature T, and this will produce a total pressure of P, which will be equal to the summation of the partial pressure, that is Pa and Pb. This is the concept of partial pressure. Now, this partial pressure can also be calculated. Now, suppose Na amount of gas A with partial pressure Pa is mixed with Nb amount of gas B with partial pressure Pb. Therefore, the mixture that we have created, the total pressure of the mixture will be equals to capital P. Now, the total number of mole of the mixture will be N equals to Na plus Nb. Now, according to the ideal gas equation, you can write P V equals to nRT. Now, the mixing is happening in the same volume at the same temperature. That's why the pressure and volume is not changing. And for the individual gases, Pa, V, Na, RT. Also, P, B, V equals to Nb, RT. Now, this is equation 1, this is equation 2, and this is equation 3. Now, by simply dividing equation 2 by the equation 1, you can get PAV divided by P equals to NART divided by nRT, or Pa by of total pressure P equals to N of A, number of mole of A divided by the total mole of the mixture N. Now, we know that Na by A, number of mole of a certain component by the total number of mole of a mixture, is nothing but the mole fraction of that component. So, we can write that Pa by total pressure P equals to mole fraction of A, or Pa equals to mole fraction of A into total pressure P. Thus, we can calculate the partial pressure of a gas in a mixture of gas if we know the mole fraction of the gas and the total pressure of the gas. In similar way, we can find the partial pressure of the component gas B equals to mole fraction of component gas B in the mixture multiplied the total pressure of the mixture.